Good afternoon. Am I audible? Yes, so we are going to solve few numericals today related to our specific energy. Okay. First, you tell me, have we discussed this numerical at 3.1? We have discussed this numerical. Am I audible? This numerical 3.2. Okay. This one 3.4. Okay. So we are going to discuss this numerical. Okay. We have discussed this. Okay. So you first write down the new questions. It's done. Example 3.4. So you write down the numerical, okay? If Fn is the Froude number at normal depth Yn of a rectangular channel, then we have to find out the value of Yc divided by Yn. Okay? Yc is nothing but our critical depth, and Yn is the Froude number at that particular critical depth, or you can say, sorry, for that normal depth, okay? So that critical depth divided by normal depth, we have to find out the value of critical depth divided by normal depth in terms of Froude number. Okay? In terms of Froude number. So first you write down the question. Now we are going to consider the rectangular channel. So it's given in the question. The channel is our rectangular channel. So we all know that YC expression for rectangular channel is Q square divided by G to the power 1 by 3. Okay? 1 divided by 3. So what is small q? Small q is nothing but our discharge divided by width of the channel. Okay, this we have already discussed many times. Okay, small q is nothing but discharge divided by width of the channel. Okay? So in place of discharge, we can write area into velocity. We can write area into velocity divided by capital V. It is the width of the channel. So you can further, if you want to solve, we are going to find out the area, or we are going to substitute the area equation as it is given as a rectangular channel. So that area expression will be width of the channel multiplied by depth of flow. So as we are going to consider a critical depth, so it will be YC multiplied by velocity. Sorry, it's normal depth. Okay, we are going to consider a normal depth, so it will be YN, because here it is given normal depth. Okay, so V into YN multiplied by velocity. So this part is area multiplied by velocity divided by width of the channel. So this will be cancelled out. Okay, width of the channel will be cancelled out, and then for the small q, we can write V into Yn. So here that is why in place of q, here we can see V into Yn. Okay, so this is how we can write in place of q. We can write V into Yn. So it is small q square. That is why V into Yn whole square divided by g to the power 1 by 3. Then if you further solve, then it will be v to the power 2 by 3, yn to the power 2 by 3, and g to the power 1 by 3. Okay. Now we are going back to the question and see what is going to, or what we are going to find out, or what we need to find out. That is the ratio between yc and yn. Okay. So we got this expression for yc. Okay, but we need to find out the ratio of yc divided by yn. So we divide both left hand side and right hand side by yn. Okay? If we divide by yn in the left hand side, we will get this expression. That is a ratio of critical depth divided by normal depth. Okay? So here also in the right hand side, we need to divide by yn. Okay? So this v to the power 2 by 3 will be same. G to the power 1 by 3 is also the same. If you see, we have y to the power 2 by 3 divided by yn. Okay? So it will be yn to the power 1 by 3. Okay? This is nothing but 2 by 3 minus 1. Okay? It will be minus 1 by 3, so you can write divide. Okay? So again, here if you go back to the question, what is given, that we need to find out yc by yn in terms of fn. Okay? So whatever the yc by yn we got here, here we don't have Froude number. Okay, so we need to bring that Froude number here. You all know Froude number is Froude number is p by root over g by n for rectangular channel. Okay. So here we have v, we have g, we have yn. Okay. So we can write this thing in this pattern. You see thus v to the power 2 by 3, and it's 1 by 2 multiplied by 2 by 3, we will get 1 by 3. Okay? 2 will be cancelled out. So you can write this root over gy1. Okay? And this is nothing but your problem. So in place of this, you can write f of n, odd number for normal depth to the power 2 by 3. So this is our required solution of that particular numerical. That the ratio between yc by yn in terms of fn. Okay, that is your Froude number. So that fn to the power 2 by 3 is the correct answer. Let me move on to the next numerical. This is the next numerical for you. First, you write down the question that supercritical flow occurs at Froude number Fr is equal to 2 is given at a depth y is equal to 0.60 meter in a rectangular channel. Find out the critical depth yc. So we need to find out the yc. Okay? Yc for rectangular channel is q square divided by g to the power 1 by 2. Okay? This is the expression for yc of a rectangular channel. So what is given? That Froude number is given. That is your 2. Fr is given dy root over gy. Okay? That Fr is given is equal to 2. Okay? Depth of flow is also given, that is 0.6. Okay? And we need to find out the yc value, that is your critical depth. So here that yc we have small q. Small q is nothing but discharge divided by width of the channel. Okay? Again, the discharge is not known to us. So in place of discharge, we are going to write area into velocity. Okay? Or in place of area, we can write v into v divided by, so it will be again v multiplied by y, small q. So velocity is not known to us. Y is known to us. Okay, it's given. That is 0.63. So from this Froude number equation, you can find out the velocity here from this equation. As your Froude number is already known to us, it's given. That is your 2 meter. Sorry, it's a 2. And velocity is not known to us. Acceleration due to gravity is 9.81. Okay, multiplied by depth of flow. Depth of flow is given 0.62. Using this expression, you can find out the velocity easily. So find out the velocity, then you substitute here, you find out the small q, then that small q you substitute in this critical depth formula, okay, and then you find out the YC value. Find out and see the value you are going to get is almost equal to 1 meter. Now how much we got Y value, YC value? We are getting 1 meter. If you have completed this problem, then we will move on to the next one. Okay. So this is our next numerical. Discharge. The discharge of 16 meter cube per second flows in 8-meter wide rectangular channel. So in a rectangular channel, the width of the channel is given 8 meter. Then discharge is also given is 16 meter cube per second. Rectangular channel under critical condition of flow. So we need to find out YC, that is your critical depth, and specific energy corresponding to this critical depth. Okay. Then at last we need to find out the critical slope SC using your Manning's equation. Okay, because your Manning's n is given, so we are going to find out the critical slope using the Manning's equation. So that discharge is given, width of the channel is also given. So you can directly find out the small q, that is q by b. So you can directly find out the q by b. And then you use that YC expression for rectangular channel. Q square divided by G to the power 1 by 2. Okay? To the power 1 by 2. And up to YC value, you will be getting around 0.741 meter. Then after that, you find out the corresponding specific energy for that particular depth. Or how much you got YC value? So once you find out the YC value, then we need to find out the specific energy corresponding to that particular depth. That is your critical depth. That specific energy, we have already derived this expression. If you want, you can directly use the general expression also to find out the EC value. That is your YC plus V square by YZ. Okay, you can use this one. Okay, you can also use this equation to find out the EC value, or you can directly use this one. It's up to you. EC is equal to 3 by 2 YC. Okay, we have already derived this expression, so we are going to use this expression to find out the EC. We'll be getting the specific energy will be 1.11 meter of water. Okay, so this is our first part of the numerical. The second part, we need to find out the critical slope. We need to find out the critical slope using Manning's equation, because the Manning's n is given to us. Okay, so we are going to use Manning's equation to find out the critical slope. So I think we have discussed that Manning's equation. Already we have discussed this Manning's equation. So you directly use that Manning's equation. 1 by n r to the power 2 by 3 sb to the power half. That SC we are going to consider as we are talking about critical flow condition. So in place of SB, we are going to consider critical slope. So velocity, we can, as we know, for critical flow condition, your flood number is equal to 1. So we know flood number is nothing but Vy root over Gy. For critical flow, it will be YC. This flood number is equal to 1 for critical flow condition. So in place of velocity, you can write this expression. Root over GYC. YC we have already calculated. So you can substitute here and you can find out the velocity easily. Okay. So that is why in place of velocity, we have substituted this expression, that is root over GYC. Okay. N value is already given. R is A by P. You need to find out the area and weighted perimeter of a rectangular channel, where width of the channel is already given, and the depth of flow, that is your critical depth of flow, we have already calculated, that is 0.741. Okay. Depth of sorry, width of the channel is given 8 meter. So you can easily find out the area and weighted perimeter to the power 2 by 3, then SC to the power half. So from this equation, you can easily find out the SC value. Okay. So you solve for SC and C, you are getting the same value or not. It is 0.003045. How much you got for critical slope? You're getting the same value 0.003045. Okay, so we are going to end this meeting here. So in the next class, we are going to derive for hydraulic exponent, small derivation for your critical flow. And then we solve one or two numericals more, and then we move on to our next unit. That is our gradually varied flow. So we are going to end our class today here.